And it has a value of 6.67 times 10 to the negative 11. Very small. It has units. The units are Newton meters squared per kilogram squared. Kind of ridiculous set of units, but those are them. Big M is the mass of object 1, whatever it is. Little m is the mass of object 2. And r is the distance between their centers. So let's do this. Do a bunch of examples, and then I'll set you free to play with this stuff. So first example, the force of gravity exerted on a 70-kilogram astronaut standing on the Earth's surface. So let's zoom this thing in and take a look. Before, when we did this thing, if I asked you to find the force of gravity on an astronaut, a 70-kilogram astronaut, like a couple days ago, you'd say, okay, well, Fg equals mg. You would say, well, the mass of the astronaut is 70. G at or near the surface of, or little g at or near the surface of Earth is 9.81. And you would say, okay, well, here's my calculator. 70 times 9.81 equals 686.7. And you'd call her good. Well, now, using Newton's law of universal gravitation, we're going to look at this again. Say, okay, well, Fg is now equal to G big M little m over R squared. You can see that these two equations are kind of similar. Both of them have the mass of our astronaut in there. Now we can go through now and we can fill this thing out. Big G is 6.67 times 10 to the negative 11. Big M is going to be the mass of the Earth. Is 5.98 times 10 to the 24. 5.98 times 10 to the 24. That little m is going to be the mass of our astronaut. It's going to be 70. And we're going to divide that thing by the distance between their centers. Now the radius of Earth is 6.38 times 10 to the 6 meters. So that's the distance from the center of the Earth to the surface. The astronaut is standing on the Earth's surface. We don't know how tall the astronaut is. But typically your center of mass is, and we also don't know if it's male or female astronaut. That changes the center of mass. Women, your center of mass is typically lower than guys' center of mass, just because of the way guys are physically built different. The broader shoulders raise the guy's mass, center of mass. Your wider hips lower yours, just biology. So it doesn't actually matter. We'll assume that, given that the Earth has a radius of 6,380,000 meters, we're going to assume that the 1.5 meters added by the astronaut isn't going to impact much. So we're just going to use this value. And you got to make sure you square it. This is the mistake I see all the time on this chapter test. This is going to be a common mistake. It always is. Don't make it. So 6.38 times 10 to the 6, and we're going to end up squaring that thing. You're going to want to be comfortable with scientific notation on your calculator. If you ram that thing through, and I would encourage you to try it, make sure you get the same value I do. 10 to the negative 11. Because the exercise in punching this thing in is useful. 5.98 times 10 to the 24 times 70 divided by, set of brackets, 6.38 times 10 to the 6, close my brackets, square it. You're going to want to get comfortable with however your calculator does this. The Casio's, it's going to end up looking like this. It takes some time. But get a handle on how your calculator behaves. If any of you are blessed with enough to have a graphing calculator, this is the first time it's actually going to be super useful. 5.98 times 10 to the 24 is 70, and we're going to divide that by this, and make sure you square it at the end. And I got 685.94. So we had, using Fg equals mg, we had this value, 686.7. Using universal gravitation, we get 685.94. Are those sufficiently close? I would say yes. They round to almost the same, like they're out by 1 Newton. When the force is 686.7 and this one's 685.9, that's basically 687. This is 686. When you're out by 1 Newton, you're okay. So where's the issue here? Why are those values not identical? Yeah. Sorry? Part of it. There's the extra the extra meter in there. It's only going to change this by a small fraction. It's part of it though. This number is an approximation. This 6.38 times 10 to the 6. The Earth is not a sphere. The Earth is, it's called an oblate spheroid. I mean, it means if you shrunk it to the size of a ping pong ball, it would be more spherical than the ping pong ball. But because the Earth spins, it's actually chubbier at the center. The equator is, the distance from the center of the Earth to the equator is bigger than the distance from the center of the Earth to the North Pole, just because of the spin of the Earth. So you've got this effect in there where this is the average distance from the center to the outside. And that's the biggest impact there. This is 9.81, that's also a rounded value. So we've got approximations in both of these that lead us to not having exactly the same answer. But as far as the physics goes, this is good enough. What this equation doesn't let us do is handle things like this. We're going to take our astronaut and we're going to raise them to an altitude of 6.38 times 10 to the 6 meters. So the distance from the center of the Earth to the surface is this. And now we're going to take that astronaut and we're going to raise them another 6 million meters. So we've got this situation happening here. We've got the Earth, and way out here, so actually I should draw it to scale. That distance there is this value here. If we take our astronaut and move it, that same distance away from the surface, as you move away from a massive object, the effect of its gravity decreases. And just to put that into perspective, this is well, as far as I can tell, there's nothing out there. This is going to be well past any orbiting satellites. They're going to be here-ish. So, but there's our astronaut. What's the force of gravity on them? Well, Fg. Now we have to use universal gravitation. This is only good at or near the Earth's surface. So Fg is going to be equal to gmm over r squared. And that's going to be 6.67 times 10 to the negative 11. This value you do not have to memorize. It's on your formula sheet. The mass of the Earth is 5.98 times 10 to the 24. Also on your formula sheet. The mass of our astronaut is 70. Not on the formula sheet. And we're going to divide that now by what value? What's going to go in here? Is the person on the surface of the Earth? We have to add these two values together. It just so happens these two values are the same. So the way we could put it in here is we could say, well, we're actually going to have 2 times the 6.38 times 10 to the 6. Because these two values are the same, we can just double this. And then it actually makes our calculation a little bit easier. And depending on the kind of calculator you have, if you have a graphing calculator, it's easy to bring this back. For those of us who don't have a graphing calculator, we're punching it all in again. I want this one. 6.67 times 10 to the negative 11. 5.98 times 10 to the 24. 70 divided by 2 times 6.38 times 10 to the 6. And we're squaring that thing. What do we get? What is the force of gravity on that astronaut? 171.48 newtons, you bet. Oh, I lied about something earlier. When I told you there was nothing out here, that's not true. Hands up if you've ever heard of a geosynchronous orbit. That's a word that you've ever heard of. Geosynchronous. Okay, so there are satellites that are in orbit above the Earth such that they move at the same speed as the ground underneath them. So like a US spy satellite might want to be in geosynchronous orbit because it wants to photograph the same area for a while. Those satellites are actually going to be way the heck out here, really far away. So there is stuff in this distance between our astronaut and all those objects further out yet. My bad. But this is now how you have to calculate this. Astronaut is not at or near the surface of the planet. We have to use universal gravitation. Yes, here. Say that again. Yeah. Sorry. Where's the moon? If this is um, 60 of these lines away. So if this is to scale, the moon's over here somewhere. Like really far away. Sorry? Yeah, if this is, like, so not looking at it on the screen. like on my page, if this is 6,380 kilometers. This is 6,380 kilometers. The moon is 60-ish, almost 60 of these lines away. So on my paper to scale, it's going to be over here somewhere. No, I'm pointing over here by where my power bar is next to the wall. The distance between the moon and the surface of the Earth is pretty impressive. Okay, next one. The ultimate physics pickup line. Two physics lab partners sit side by side. One has a mass of 55 kilograms and the other has a mass of 65. If they sit 50 centimeters apart, what is the irresistible force of attraction between them? So here we go. The gravity, the force of gravity between two physics lab partners. GMM over R squared. And to put this into perspective, where's my meter stick? 50 centimeters apart is not shoulder to hip. It's not sitting shoulder to shoulder. It's from the center to the center. So if you're sitting 50 centimeters apart, Vine, you got to scooch in a little bit. No, Vine, you got to scooch in a little bit more. Okay, this is the scenario existing in that question. So that 50 centimeters needs to be center to center. So if I just look at the center of their backs, this is the situation. What is the force of gravity between Liam and Vine, assuming those are their masses? Okay, you guys can stop sitting quite so close together. So, universal gravitation hasn't changed. 6.67 times 10 to the negative 11. The mass of one is 55, the mass of the other one is 65. The distance is half a meter. This always needs to get converted. There's 100 centimeters in the meter, so divide that by 100, you get your half a meter. And don't forget, we've got to square that value. What is the force of gravity between Liam and Vine sitting shoulder to shoulder? Obviously not very big because they were able to slide apart fairly easily. What's that value? This one's a lot easier to punch into your calculator. What'd you get, Lena? Okay, one more time. 0, 0. 6 zeros. Okay. 953. Is that where your calculator ends? Okay. What'd you get here today? You bet. Not 0, but it may as well be. And it has everything to do with the fact that these masses are really small. Okay, so 2 more of these and we'll call it a day. So these are typical problems of this nature. It could look like this. If you've got an astronaut that weighs 800 newtons. Now remember, there is or for those of you who weren't here, there is a difference between mass and weight. Mass is all of the parts that make you up. It's measured in kilograms. Your mass does not change regardless of where I put you in the universe. To change your mass, I'd have to chop you up. Your weight, though, is allowed to change. Your weight, this word weight, or weighs, is the interaction between a mass and gravity. That is what weight is. We call this FG. The interaction between a mass and a gravitational field is FG. So when this says weighs 800 newtons on planet X, what they're giving you is the force of gravity this astronaut is experiencing at some location in the universe. That's their FG, somewhere. And the question then says, how much would she weigh if she was at an altitude equal to the radius of planet X? So here's the question. We've got planet X right here. We don't actually know what the radius is. So let's just draw it, and we'll call that radius X. I'm not going to use R because R is part of the formula, and if you use R in multiple spots, it's really easy to get confused. So we'll call that X. What we're going to do is we're going to take this person, and we are going to move her a distance of X above the surface. So now the distance from her center to the center of planet X isn't X anymore, it's 2X, or X plus X. And we want to figure out what FG is on her at this location. We know that if her FG on the surface is 800, we know that this is going to be equal to GMM over X squared. We don't know what the mass of the planet is. We don't know what her mass is. We don't know how big the planet itself is, but we do know that regardless of these three values at the surface, or a distance X from the center to the surface, she has a weight of 800 newtons. So the question is going to become, what happens when we double this? So let's double this. We're going to get GMM. Now, instead of over X squared, it's going to be over 2X squared. And all I'm going to do is I'm going to apply one of the exponent laws that you learned in grade 8. And we're going to say, okay, well, if I've got two things multiplied together inside this set of brackets, I can apply that squared onto both of them. What that's going to give us is it's going to look like this. GMM over 4X squared. All I did was apply this exponent to both of those pieces. 2 squared is 4, and X squared is just X squared. But we know what a chunk of this is equal to. We know that this piece here, regardless of all those values, GMM over X squared is equal to what? 800 newtons. So then her force of gravity out here is just equal to this orange box, 800 over 4. So doubling the distance quarters the force of gravity on a person, well, on any object. Doubling the distance between two centers quarters the distance. So now FG on her at that point, 800 over 4 is 200. Don't know what the mass of the planet is, don't know what her mass is, don't know what that distance is. We just know that if we double it, the force of gravity is going to quarter. Comments, questions, concerns about what I've just done? Yeah. Why is this? Okay, because we were that all of this is packed into this statement. Oh, actually, I need one more word. An astronaut weighs 800 newtons on. So on, wherever, means at the surface, which means this distance from the center to the surface is well, we don't know the value, but that's what we're going to call X. So all of this, the fact that GMM over x squared is equal to 800 is packed into that first portion of that sentence. And we don't know any of these values, so we're just going to use variables for all of them, mm over x squared. Then we're told to double it, and so that's where this came in. Does that help at all here, Day? Okay. So we'll do one more like this. It's a similar idea, except we're going to change a few more things. We've got a spaceship orbiting a planet of or at radius r. It has a weight of 10,000 newtons. How much would it weigh if it orbits a planet that is twice as, so we take the rocket and we move it to a planet twice as big, and we have the radius. We move it closer to a larger planet. It's the same kind of idea. All we're going to end up doing is fiddling with these values. So here's what we've got. A spaceship orbits a planet at radius r. So we know that FG for this spaceship, that word weighs means that that's equal to FG. And now I can just pack our new universal law for gravitation in here. So we got big G, the mass of the planet, which I'll call MP, the mass of the rocket, which I'll call MR, all over. It says it orbits a planet of radius r, or at radius r. So it's not at, when it says at radius r, that is not the radius of the planet. That is the radius of the orbit. And radius of the orbit is always measured from the center of the planet to the center of the orbiting object. Center of planet to the object is what that means. Well, they gave us a letter already, so let's use it, even though it's kind of messy. So we've got G, mass of the planet, mass of the rocket, over r squared, the radius of the orbit. What we're going to do now is we're going to double the mass of the planet and have the radius of the orbit. So this is going to become, what's going to happen then when we do this? Big G stays the same. It's the universal gravitational constant. Doesn't matter where you are in the universe. This value is true. And it's actually one of the most precisely known experimental values we've ever done as a human race. So that's G. The mass of the planet is now doubling. So we're going to have 2 times the mass of the planet. The mass of the rocket hasn't changed. And we're going to have half, or 0.5, r in brackets squared. So what's this going to do? Well, it's the same kind of exercise that we went about in this example here on the left. I'm going to take this 2 and I'm going to move it out front. I'm going to apply this exponent onto both of these things down here. And then I'm going to take whatever I have out here and interact it with the 2. So we're going to get 2g times the mass of the planet, the mass of the rocket, over. Now I'm going to have 0.5 squared times r squared. This portion of the problem doesn't change. This is g, mass of the planet, mass of the rocket, over r squared. This has a known value. It's right there. This now is this. So we're going to have 2 times 10,000 over 0.5 squared. If you do that, what do you get? You have a value, Lena? No. 80,000. So the rocket experiences being heavier. at this new location? Questions, comments, concerns about what I've just done? Okay, cool. So, welcome to Newton's universal law of gravitation. I want you to play with this. I want you to do the following questions. I want you to do 1 to 6. I want you to do question number 1 to 6 and number 11. That's what I want you guys to tackle. The answers are down there at the bottom. They are in order. Comments, questions, concerns, let me know.